Hello friends, warm welcome in this video, that is the mechanism of catalysis. So friends, what is catalysis or what is a catalyst? A catalyst accelerates a chemical reaction without changing its extent and can be removed unchanged from amongst the end products of the reaction. It has no overall thermodynamic effect. The amount of free energy liberated or taken up when a reaction has been completed will be the same whenever a catalyst is present or not. In most cases, a catalyst acts by reducing the energy of activation. The catalyst or part of it combines with the reactants to form a different transition state from that involved in uncatalyzed reactions, one which is more stable and therefore of lower energy. We should note that the initial and final states are at the same free energy levels for the catalyzed and uncatalyzed reactions, and the overall free energy change as the reaction proceeds is also the same. As a rough generalization, therefore, an uncatalyzed reaction might proceed as follows. A plus B with a very slow rate converts into AB, which is converts into products with very fast speed. The same reaction, but in the presence of a catalyst C, might take place like this. A plus B plus catalyst C, which is a fast process, which converts it into ABC, which again converts into products plus C with a fast rate. Because the catalyst stabilizes the transition state, the breakdown of the intermediate to the products might be slower than in the uncatalyzed reactions. Nevertheless, the overall rate is determined by the slowest step in the sequence, so the overall rate of the catalyzed reactions will be faster than for the uncatalyzed reactions. Of course, most of the reactions are reversible, but we should note that the activation energy required for the reverse energetically unfavorable reaction is energy required to form the transition state from the products and is thus much greater than the activation energy in the energetically favorable direction. The proportion of colliding product molecules possessing between them sufficient energy to overcome the potential barrier will be even less than for the reactants. However, the greater the product concentration, the greater the number of molecules present capable of undergoing the reverse reaction. The overall trend indicated by delta G towards chemical equilibrium depends on the actual concentration of reactants and products present. The position of a chemical equilibrium is not affected by the presence of a catalyst. The catalyst merely accelerates its attainment. The mechanism of catalysis involves various types of catalysis. The very first type of catalysis is the acid-base catalysis. Acid can catalyze reaction by temporarily donating a proton. Base can do the same by temporarily accepting a proton. For example, in this case of hydrolysis of ester, the transition state is stabilized by base XO. Bases may also increase reaction rates by increase the nucleophilic character of the attacking groups. Thus, hydroxide ions displace halide from alkyl halides more rapidly than do neutral water molecules. Similarly, acids facilitates the removal of leaving groups where these are strong bases. For example, in the following reaction, which would normally proceed extremely slowly, but in the presence of acid, however, conditions are more favorable and the reaction will proceed rapidly. Similarly, in the case of ester hydrolysis, protonation of substrate leads to a transition state which avoids the unstable two-charge arrangement occurring under neutral conditions, thus increasing the rate of reaction. In general, acid or base catalysis may be shown to be operating by determining the rate constant of a reaction at different concentration of acid or base. The second type of mechanism of catalysis is electrostatic catalysis. A transition state may be stabilized by electrostatic interaction between its charge groups and charge groups on catalysts. Thus, the positive charge on a carbonium ion can be stabilized by interaction with negatively charged carboxylate ion. Similarly, the negative charge on an oxygen can be stabilized by positively charged metal ion. For example, the hydrolysis of a methyl ester of a glycine to produce glycine and methanol may be catalyzed by cupric ions. The mechanism probably involves the following steps. The third type of catalysis is covalent catalysis. In contrast to acid-base and electrostatic catalysis, where the transition state is merely modified, covalent catalysis introduces a different reaction mechanism and is sometimes termed as alternative pathway catalysis. In the case of nucleophilic catalysis, the catalyst is more nucleophilic than the normal attacking groups and so rapidly forms an intermediate which itself rapidly breaks down to give the product. For example, Myron Bender and co-workers in 1957 showed that a variety of tertiary amines catalyzes the hydrolysis of esters as shown in this figure. In contrast to electrophilic catalysts act by withdrawing electrons from the reaction center of an intermediate and may be termed as electron sink. This type of catalysis is found in the reaction of the coenzymes thiamine pyrophosphate and pyridoxal phosphate. Sometimes metal ions may also be regarded as acting in this way, where metal ion facilitates the withdrawal of electrons from reacting carbon atom. The last but not least mechanism of catalysis is enzyme catalysis. All the earlier mechanisms of catalysis are seen in enzyme catalyzer reactions. However, enzymes, because of their great size and range of properties, are able to impose their presence on a reaction to far greater extent than most catalysts. All catalysts act by reducing the energy of activation, or more correctly, the free energy of activation, that is delta G hash, of the reaction being catalyzed. Free energy is made up of an entropic and enthalpic components. Since delta G is equal to delta H minus T delta S, hence delta G hash is equal to delta H hash minus T delta S hash, where delta H is the enthalpy of activation and delta S hash is the entropy of activation. And so anything which decreases delta H hash or which makes delta S hash more positive will lower the value of delta G hash and help the reaction proceed. There is a great loss of entropy when reactants lose their random existence in free solution to become bound in the transition state. So minus T delta S hash will generally have a large positive value, possibly making up about half of the total free energy of activation where is more than one reactant. In enzyme catalyzer reactions, there is inevitably similar loss of entropy at some stage, but it occurs largely in the binding steps when enzyme substrate complex are formed and not to the same degree in the actual conversion of substrate to products. The binding of substrate molecules in close proximity to each other on the enzyme surface effectively increases their concentration and reduces the entropy loss of the subsequent formation of a transition state. This has been called the approximation effect, the approximation effect, and or the propinquity effect by Thomas Bruce, William Jenks, and others. The enzyme may also ensure that the reacting groups of the bound substrate approach each other with their electronic orbitals correctly oriented, thus ensuring that the reaction takes place under optimal conditions. Daniel Kostland termed this property of enzyme orbital steering. The contribution of catalytic sites on the enzyme to the reaction will generally be to the enthalpy factor by stabilizing the transition state. It appears that stability of enzyme bound transition state may be the most important single factor in determining whether the reaction proceeds. It is possible that several different catalytic processes may be involved in the same enzyme catalyzer reactions, as may be seen in the earlier example. Another way in which the enthalpy factor may be reduced occurs if the positions of the binding sites on the enzyme do not correspond exactly to on a substrate. As the substrate binds, some of its bonds may be distorted and weakened, resembling those found in transition state. This is the hardening and Pauling concept of strain, I discussed earlier video. Alternatively, the enzyme substrate complex may be under stress from internal interactions which are absent from the enzyme bound transition state complex. Again, this would be facilitates the forward reaction. A distortion of protein to fit the substrate would have no effect on enthalpy, but it would not preclude stress factors from playing a some reactions proceeds better in organic rather than aqueous solutions. Most enzymes contain regions of non-polar character, and these may be of important in catalysis of such reactions. So enzymes create a suitable environment for the reaction to proceed. They reduce the total free energy of activation required and also spread out the free energy requirement over several stages. Nevertheless, some activation energy is still required for each stage of the reaction sequence. This cannot come from the substrate because the transitional energy that dispatches in free solution is lost the moment they become bound to the enzyme. It seems likely that the required energy is obtained from collision between solid molecules and the enzyme substrate complex, but the mechanism for this is far from clear. Thank you.